Hello and welcome back to another episode of Natural Number Game with Lean 4. Last time we ended up proving and or distributed on the left side. That was a lot of fun. That got us complicated proof. Today we'll be finishing up the advanced proposition world, starting by proofs by contradiction. So, for example, it's certainly true that P and not P implies Q for any propositions P and Q. Because the left side of the implication is false, we can't have both P and not P be true. And so today we're gonna prove that lemma contra with P and Q propositions, P and not P implies Q. And we're gonna do that how? First we can introduce P not P, or P and not P. And then from here we can get P from P and not P dot left. Let not P equals P and not P dot right. Sorry. Okay, so we have P and not P, and we want to prove that we get Q from this. And how can we do this? So the first thing that we can do is rewrite from we can turn not P into P implies false using not if and only if implies false. How do we do imports again? Let's look at multiplication world. Import, okay. We're gonna import dot proposition world. Now we have access to this. Yes. Okay. Add not P. Sorry. Okay, so we went from this to this. Great. Now we want to get Q. And from false, everything's true, so we could false be defined as not P of P, and we have this tactic false, or we have this constructor false dot elim, which we can just pass false into. And if we look at false dot elim, it says if we pass in false, we can get any proposition. So it says from false, any desired proposition C holds. And this is the whole ex falso, or principle of explosion. And yeah. So this solves it, and there's and then actually one cool thing is we didn't actually need this rewrite because not P is P implies false by definition. So we didn't even need to do the rewrite. This still works. And there's another way to do this with comment this out as well. Oops. Exact absurd. So you can see absurd. Anything follows from two contradictory hypotheses. For example, Lola, absurd, HP, HPN. And so, oh, that's a cool link. And then, so with this, if we just pass in two contradictory hypotheses, it'll be true. So absurd, P not P. Or here we also do not PP, not PP. Okay, we actually want to do P, not P. And then this also says by contradiction, this absurd thing, anything follows from two contradictory hypotheses. And this is another way to solve this contradiction lemma. Great. That is the advanced proposition world, and now let's move on, or level 9, now let's move on to level 10, the law of the excluded middle. So we proved earlier that P implies Q implies not Q implies not P. We did that in the proposition world. Where do we do that? Yeah, we do that here. Contrapositive. We conclude P implies Q implies not Q implies not P. Now we're gonna do the reverse of that. So, or the converse of that. Specifically, lemma, we're gonna have contrapositive 2. If contrapositive was so good, why isn't there contrapositive 2? Contrapositive 2, not Q implies not P, don't need the space, implies P implies Q. Sorry. Let's move this onto this line. And how are we gonna do this? So proving this using what we've learned so far is impossible because this is not provable in constructive logic. So if we intro PH, and we try to use or if we use not, but if we just look at sorry here, we can see that we need to prove Q from this. So our hypothesis is P. And then our P is, actually I'll probably switch these names around. This seems kind of confusing. PH. HP, does it matter? Yeah, there we go. Intro H, intro P. Hypothesis is not Q implies not P. And our proposition is, and P is P. So how do we progress? We can't really. Apparently the tools we have are not such to continue, but we can prove this using the by cases tactic from Lean 3. Is there something similar in Lean 4? By cases. Oh, seems to be. Okay. By cases splits the main goal into two cases, assuming HP in the first branch and H not P in the second branch. Aha, okay, that seems promising. Okay. By cases P, by cases Q, Q. Sorry. Okay. Unresolved. Oh, do multiple sorries? We have multiple things. Sorry. Too many sorries. Okay. So we have 3 cases. Case inline, or okay. So let's think I can replace these with tag and all. Something like this. This does not seem to be working. Okay, let's figure out cases. Oh, maybe width. I'll need to look into how to do some of this syntax stuff. Okay, so let's go into 2 cases. Okay, so I was able to figure out how to do this by looking at some resources online. But I can do this with case INL, sorry, and case INR, sorry. And then in this case we have P, and here we have not P for what happens with P. And we can do something similar with cases by cases Q. Case INL, sorry, case INR, sorry. And then these dots, all they do is help for formatting, else this would be inline. So this is fine. Oops. Yeah, the dots just help stuff with like formatting. And here we see we have Q, and here we have not Q. And so we do something similar here. By cases Q, case I. Let's do this. Sorry. Sorry. Okay, so this pretty much turns into all 4 things. So you have PQ, P not Q, not PQ, not P not Q. And now we can prove these. Just like systematically turns into all 4 possible truth combinations. Okay, so now what do we want to do? Now we want to just prove this. Okay, and remember, so not something is just given Q get false. So I don't know what the easiest one is. Well, okay, this one's pretty easy. Exact Q. Okay. What about this one? We want Q. Well, what happens if we apply H, HQ, or let F equals, can I do HQ, not P? Okay, so H of Q is not P, so we could do absurd HQP. Exact. Oops, we want to do P first. Do we need the exact? Yes. Okay. And this is kind of what we did before. So at this point, we both have not P and P. We have not P by passing Q into our hypothesis. we solve that case. Okay, now let's move on to the next two. So what do we have here? We want to get Q. Well, we just have Q. Exact Q. And then here, actually, I think we want to name P. No. INR P1 P2. Okay, nice. So P1 here is P, because in this case we just have, can I just call you P? Guess this will be clear. This is P and this is not P. Okay, so here we have P and not P in this case, or okay, this P. P1. Let's call it P prime. Why is not PP as well here? Not too sure why in both this case and this case P prime. Okay, yes, P just takes on both values. Okay, by cases, something P splits the hypothesis. Two cases, some P in the first branch and not P in the second branch. Well, regardless, we have P and not P here. So we can just do exact absurd P prime P. Great, and that solves contrapositive 2. And yeah, and with all of that we have contrapositive and contrapositive 2, and we have the rest of the advanced proposition world solved. Let's add one more lemma. Full contrapositive and then we'll have this be if and only if. How do we deal with if and only ifs again? We want to constructor constructor. Okay. Exact contrapositive, exact contrapositive 2. Should be this one first. Okay, what's going on here? Oops, do we need... I thought we should do constructor and then exact. And we have both of our cases. What went wrong here? Contrapositive. Okay, so has type for all PQ. Oh, okay, that is wrong. So 2. Huh. Aren't these similar? There we go. Okay, we just need to apply it to the specific PQs. Q. Nice, and that's our full contrapositive lemma. And yep, that concludes Advanced Proposition World. Next time we'll be working on, let's see, the Advanced Multiplication World. Advanced Addition World. We'll do the Advanced Addition World. Thanks so much for watching, and I hope you enjoyed. Goodbye.